Welcome back. So the last speaker of the day is Gianpietro Pirola. He will speak on holomorphic one form on the modular space of curves.
Thank you. First of all, let me thank the organizer to give this opportunity, and in particular Professor Biswas, and also because the topic of his problem comes after a discussion with him. Is about one form on G. So let me start with one holomorphic form. G. So I'd like to start with some history and motivations. And and I think the history starts with Mumford, the paper, a famous paper in 62, when he computed, now we'll be more precise, but H1 of NG Z. So we know already that we have seen that MG is the moduli space of curve of genus G, and I take over the complex. And we assume that G is bigger than 4, but G bigger than 3 will be enough for us. But later, maybe it makes things easier. And also, let me define two space, MG0, which is the curve without automorphism, and the Riemann-Mumford compactification. So MG0 is the set of curves with the automorphism of C is 1. And because G is bigger than 3, this is, and the smooth locus of MG. So this also allows me to avoid any problem with Kuranesi family or orbifold, because this is an open orbifold, open set, stack, if you like. And MG bar, the Riemann-Mumford compactification, is MG union delta 0 union delta 1 union delta the integral part of G half, where delta 0, the general point, they are a stable curve, nodal stable curve. The general point, delta 0 is just one node irreducible, and delta I is a curve of genus, general point. Maybe let me write down in the real. This is of genus 1, genus I, and this of genus G minus I. Okay, and what Mumford proved. Essentially is that H1 of MG0 Z, I think, that's to be safe, but I think is 0, also over Z. And let me remark that when G is bigger than 3, because we threw away the hyperelliptic locus, mg minus mg0, so the complementary, has codimension in mg bigger or equal than 2. So the fundamental group of mg0 is the mapping class group just because if you take the Teichmüller and you go to mg, and then this is a discrete map, and you take the inverse image of TG0, you remove here something codimension 2, and so it becomes the tal, and the group is this one. And in fact, he proved that gamma G is everything, I think. This is the result of Mumford was precise, was made a little more precise by Harrer later. But I think he proved. I think. And also Harrer proved that also give proof that H2 of mg bar over Z is generated by the class, the HODGE classes, and plus the class of the boundary, the divisor of the boundary. The C1 of the HODGE bundle, called the HODGE class. So you have the HODGE bundle in the, yeah. So the C1 of the HODGE bundle. I call the HODGE class. Maybe I make it, it's not so correct. Thank you. Okay, so in particular, from Mumford, you obtain that H0, the closed form, because R, the holomorphic form, are equal to the exact form. On the other hand, let's say corollary. The second corollary, it was at the time quite important, that the Albanese variety of mg bar, or if you like, from the singularization is 0. But then also one has easily, I think also he did, that H0 of the exact form is 0. And this follows easily from another compactification. This is the Tate compactification. I do this a little in detail because the same kind of argument is used in our result. The second compactification, you use the period map, or the map on AG. Here we have a Tate compactification. And then you take the image here and take the closure. Take, and the point in the boundary. And also there is a map, let me say, is better. From the Deligne-Mumford the Satake compactification. And this map to, let's say, AG Satake gives us the map from the curve C to the Jacobian of the normalization. Of C. But this Satake compactification is like AG union AG minus 1 and so on. And this is the product of some curve. And you take the normalization, which is a compact abelian variety, principal polarized. And one remark that this is smaller, is the minimal, is the last compactification possible. Although maybe it's not a modular one. But what is interesting is that if you look at the map from delta I to, you take this map, so the fiber, when I is different from 1, is a surface. For instance, generically. Because if you have something like this, essentially the same, if you move this point either on C or you glue in 2 different points, you have the same Jacobian. So the surface goes to the same abelian variety. And the same when you go to the, but in the case of delta 1, this will make delta 1, the elliptic, the point in the elliptic curve does not count because there is the automorphism of the elliptic curve. And so the fiber here, generically, the fiber is a curve. And this is essentially the curve of genus G minus 1. You can move the point in the curve of genus G minus 1. And in any case, what you have what happens is that we take mg Satake compactification minus mg, the codimension is 2. And it would be 3 if there is no delta 1, but it's 2 because of this. And also we know that Satake compactification is projective. So it is projective, the Satake compactification of AG. So if you take 3G minus 2 hyperplane, you can find complete curve in MG. And also in MG0, because we threw away, we are genus bigger than 4, also MG0. And also in MG0, which is in codimension 2 also, because G is bigger than, so a complete curve in MG. Also, we can take that passing through 2 general points. You can do it in many ways. A point and the tangent as you like. You cut with hyperplane. If it's not good enough, you can take a multiple of this embedding and find the hyperplane that cut from 2 points and avoid the codimension 2 locus. Then what happens in that there are no holomorphic functions because for any 2 points there is a complete curve, and so must be constant, must be the same, the function must have the same value in the 2 points. And from this is equivalent to say that H0 of omega 1 exact is equal to 0. Okay. Then we can say that this is 0. And our aim is to remove the closed condition. And this comes, as I told you, with a discussion with Professor Biswas regarding some problem on making more precise relation between one form on moduli space and projective structure. I don't think I have time to say something here, but maybe I don't know if Paola will say something, but I don't. Anyway, there is some. Okay. So let me say our theorem. This theorem is by Favale and then myself and Torelli. That is not the original one, but and there is okay. And the second, the theorem says that it's 0 of mg 0 omega 1 and G0 is 0. There is a second theorem. So F, well, there is an adjoint, it's Naranco. And well, it's a little more complicated, but say that there is a locus at Zariski, open. Locus, there second paper, locus open, not trivial, of the prime locus where it's called P0, which is, it should be more or less the same as N0, but it's not completely, but such that remark that it's not so bad to prove something in a small locus here, because if you have no form in a small locus, you have no form in a bigger locus, one form. Okay. Before to go to the proof of the theorem, in particular of the theorem 1, because the second, I would like a little discuss not only mg, but some covering. Because the second result has to do with some covering of, you know, you have to take a point of order 2 in order to make covering and to construct the prime variety. So, covering. Just to say some word. Et al. Of mg0. Now, prime locus. Prime locus, you have to take a 2-to-1 et al. Covering of the curve C et al. Then you construct the Jacobian of C tilde. You take the map from the Jacobian of the curve C. You take the connected component of the identity. It is a principal polarized locus. And so the prime locus PG is inside AG minus 1. So you drop by 1. There is a little, this is not a finite map, it's a generically injective for G big enough. For some G big enough, maybe 7, I don't know, something like this. And okay, something like this. There is a construction of abelian variety that you can do with with torsion point. It's an open subset of this locus of principal polarized abelian variety. Okay. Now maybe it will be a little more clear. So you can take MG0 and you can take an étale covering finite étale covering. And I would like to mention, this is equivalent to take a subgroup of finite index of the mapping class group. And then there is a conjecture, important, Ivanov conjecture, that claim that, again, like in Mumford result, the H1 of M R this time, so it should be just torsion, is 0. Okay. If this is true, then you can do the same argument to prove that there are no closed forms. And well, this is not known, but there is a result, a theorem. This part is topological, then will be more by Boggi. There are 2 papers, distinct papers, and so 2 papers, and the second one is Putman. They claim that Ivanov conjecture hold. It is a little more general than this, but if this gamma contains the Johnson group, the Johnson group is the group generated by the then twist of a Jordan curve of non-trivial homotopy. Disconnecting curve. So these are the curves. They are the curves that are homologous to 0, but not homotopy to 0. And they are the curve responsible when you shrink it, when you do the then twist around the singularity of the delta I with I bigger than 0. This is big group, but is much smaller than the fundamental group. Is not finite index. So in this case, yeah, you know this result. In particular, when you take the 2-level structure, so if you have a compactification of M bar on Mg bar, is the delta, the Lee-Mumford compactification, that compactify our covering. If this map ramify only on delta 0, so it does not ramify exactly on delta I, then this gamma, it contains the Johnson group, because the Johnson group, when you lift, stay alive, stay there in gamma when you take the lifting. Anyway, so this is a condition. Under this condition, well, we know that there are no closed forms. Let me give another little definition, and that give also some motivation, other motivation to this kind of problem. And also it makes maybe any question? No, I don't. I'm not sure. I don't think, but no, I don't. It's not true. There are other. There are the product of two den twist of delta 0 that are in the Torelli group, but are not in the in this place. Okay. Yeah, in fact, it's not, certainly is not, that is a good, it's not of finite index, but it's not of finite index also in the Torelli group that I didn't mention. But, okay, let me give a second motivation. And I give first a definition, then the definition. We would like to make a little connection with some maybe old notion, which is, so let me give the concavity in the sense of Andreotti and Grauert. We would like to restrict the definition on P0 form. So I would like to call, let's say, X an quasi-projective variety over C, but in principle. And I would like to say that X is P0 complete. Maybe is a wrong name. I would like to call this concave, but my collaborator say, no, concave is not good. If any P0 form on X is closed. Similar, so a sort of, to make more connection with the conference, is a sort of HODGE, so the similar definition. You can give for HPQ, or PQ complete. You can give. I don't give, but you can imagine, you can guess. Yeah, but I think you can give also I take just P0, okay? And let me remark that if X is projective, then very smooth, is P0 complete for any P. This comes from Hodge theory. Okay, P0. Second remark, if X is affine, is P0 complete only for P equal to the dimension of X. Everything is close. It's still a blank. So it's a measure, a sort of a measure. If you are near to the projective or to the affine variety. And our question is if mg0 or is covering, our theorem says that mg0 is 1,0 complete. When the result that there are no exact form, there are no function non-constant, so only all the form, all the function are closed, there is 0,0 complete, means that it's 0 or MGO is C, that we have already discussed. Okay. Let me give an easy method, to see if something is, I'll just give for 1,0 completeness. Assume X is a quasi-projective. Make P the general point. Take the tangent of X and the point P, and take V a dimension 2 space. Assume there is a surface S and a map onto X, morphism, holomorphic, and assume there is a point S in S such that the differential of the tangent of S is exactly this V, and V is general. So it's general two space contained in the tangent bundle of X. If S is 1,0 complete, then X is 1,0 complete. But the proof is, you take just one form on you want to prove that this is closed, pull back pull back on S. We know that this is closed, but this you compute against two vectors, V1 and V2, but then the same form computed on X1, I don't want to. This is 0 because this is closed, but saying that something is closed is that you have to compute against any two vector, to general vector space, and then it turns out that the omega is 0. Okay? Compute. To see that something is closed, you have to compute against any two vector in the plane, a general vector in the plane, and show that this is 0. And this is so. So the basic idea is saying that for a general V there is a surface. Because you move, yeah, general means that we can move in any, we can move the surface. It's more or less, it's a criterion, but it's more or less. Okay. So the basic idea for MG, no, maybe I give first a theorem. It is a theorem that in the case of the surface, it makes possible to give an answer. So assume that S is a surface, X is a surface, E is this joint union, this joint of smooth curve is a little stronger statement. Assume there is a big line bundle, semi-ample. So we can take a multiple of these, sorry. And assume H give a map, or a multiple of H give a map from X to Pn that give an isomorphism outside E called Sx minus E. And that contract and assume that Ks plus 2E by E is less than 0. So what is important is that this space has no section, then not S but X, then S is 1, 0 complete. So we have a condition, numerical condition on these surfaces, maybe too strong, but I'll be back later, maybe, if I have time. Now we would like to apply this to MG. Again, we use the Tate compactification. So we have the Lin-Man for compactification. This goes to the Tate compactification. And we would like to intersect, this is contained in some Pn. We would like to intersect with 3G minus, so the dimension of this is 3G minus 3, a Moduli space of curve. So intersect with 3G minus 5 general hyperplane. And we can avoid everything, every boundary, but not delta 1. So take the image here, maybe call this Y, take the inverse, call this map F. So F minus 1 of Y, this is smooth by Bertini theorem, stuff like this. And is a surface, is a smooth surface. We call S. No, we call X, smooth surface. And also the intersection with the boundary, because the boundary is in codimension 2, you can make this transverse. So there are only a finite number of points, and there are a finite number of the curve that I show you when I discussed the Tate compactification of genus G minus 1. Smooth curve of genus G minus 1. So the curve, remember this curve in the moduli means that you move the elliptic curve and you fix the curve of genus G minus 1. They have the same Jacobian, and then they give the same point in the Tate. So there is A1, AN curve contracted. And this is also and you can also make the choice. You can make the choice of this surface in a way that passes through the general point, and to the general tangent, and tangent to the general tangent to the general two-dimensional space. Also we are in MG0 because we can throw away the singularity. When G is bigger than 4, no problem. We are and now we have to compute the canonical bundle of this surface, X. And we have to do this computation. And how to obtain this computation? Well, essentially, we start with the canonical, we start with this is contained in the Lin-Mumford compactification, and then we go to the Tate and we intersect with the hyperplane. So we can use several times the adjunction, but at the end, so the K of mg bar, the Lin-Mumford compactification, is something like, now I should be more precise, not to make mistake, plus minus, I am a little trouble. I think it's minus, plus or minus, I don't remember, be important. That's 2 times. I think it's something like this. Maybe it's minus. I'll see in a moment. Minus. Okay. Sorry. Then you intersect with the hyperplane, but the static compactification has nothing to do with the delta I with I bigger than 0. because delta I is in the interior part of IG. It's not in the boundary. So is on mg bar is something, is a combination of the Hodge classes and delta zero. So you intersect, but delta zero at the end does not intersect our surface E. So at the end, what happens is just that you have kx, so you have a multiple. So you have a, so all the delta I disappear, but delta 1, so is a multiple n times, so this k of s is a number that we don't know of the canonical bundle plus 2 delta 1, but is E essentially. So plus 2E plus minus 2E plus 1/2 of E. Okay. So this is what happens. K of x, thank you. Now we have to add 2E, a contract against E. So it is n times lambda plus 1/2 of E. Now we explain, okay. And I have to contract with E. This against this is 0 because the Hodge bundle in the boundary is 0. You have no, when you move the elliptic curve here, the Hodge bundle does not move, it's fixed, almost by definition, because the abelian variety is fixed, there's no variation of Hodge structure. So is 1/2 by E, which is less than 0. Let me remark, I was a little confused before, so I don't make the remark before, that this 1/2 is really important. So if delta 1 makes us in trouble because it just, the stack compactification has the image of dimension of codimension 2, the point is that there is another important fact about delta 1 is that delta 1 has automorphism. So the automorphism of the elliptic curve -1 that fixes the point. So when you add delta 1, you are out of the orbifold structure. So to have orbifold structure, you have to ramify on delta 1. And then you do the computation on the stack stuff and it becomes like this. But when you do the computation downstairs, you get the advantage of the branch because it branches exactly on delta 1, this covering. And this is the result. If delta 1 makes us trouble now, it gives back to us a good number. Because delta 0 is in codimension 3, in this attack. So there's no, if you want to do the threefold instead, so you go to the next step, everything comes down. But this is, so delta 0 is in codimension 3. The image of this attack compactification. Okay. Oh, now I have to, now I'm going to the technical part. Okay. So I have to prove that. So I have to prove the criterion for the surface. So first step, I would like to prove the following. So recall the result is like this. Sorry, this is negative because A is a contracted curve at the end. So the self-intersection is negative because they are contracted curve on the surfaces. is a family of contracted curves, disjoint contracted curve. All of these are negative. So this is negative. Then first step is we have to show that the closed form, my notation is completely, we have x minus e is s. So first step, we prove that we have an isomorphism between the form on the compact part and on A0 of x omega 1 x n e for all e for all n bigger than 0. So this is certainly a necessary condition. We have to show that this is an isomorphism. This is surjective. Isomorphism is surjective. So this is certainly a necessary condition, because if we have something which has pole on E and we remove, is an holomorphic form on the complementary. So this is the polar part. And then we have to take care of the, so we have to show that x0 of s omega s is isomorphic to x0 of x omega 1 of x. So all the form on the surface, when we have removed this curve, comes from the ambient. So the first, to show that there are no something with pole. And the second part is to take care of the singularity, essential singularity. Okay, maybe I can do just the first step. Okay. So we have to prove this. So we take the usual map. The usual map. Okay, the usual sequence. And we would like to show that the map from A0 of omega 1 of E, the co-boundary map, is injective. And this proves that A0 of omega 1 of x is as omega 1 of x is an isomorphism. Okay? So we have first to show that this is injective. Okay. For this, we use the usual map. The usual two map. One is the restriction. This is the normal. And then we have omega 1. So you have two maps. The first one is injective. we take the map that I unfortunately erased. So we have omega 1 of x restricted to E. Then we go to omega 1 of E. And then we have the conormal, O of E of minus E. Our curves are smooth, so we can have this map. Then we tensorize this by E. We have also the other map. Make a lot of. And this is just omega 1 of E. But using adjunction, this one is nothing but K of S plus 2 times E restricted to E. So this is negative, so this is no section. So the section of this space comes from this. So H0 of omega 1 X E isomorphic to this one. This is the sum. This is disjoint union of curves. So this is like this. And now yeah, we have to do the composition. Now we have to do the composition. So we have to go from this H0 of E to this H0 of omega 1 XE restricted to E. And then take the co-boundary to H1 of omega X. But this is nothing, this is, I told you, is a sum of H0 of E. And the element here, so is generated, is just C to some N. And so it's just alpha 1, alpha N element. The generator is the constant one on any of this curve. And this curve is nothing but this composition is nothing but taking the same classes of this AI by Zatia stuff or stuff. But these curves are disjoint curve with self-intersection, which is negative. So this equal to 0 implies AI equal to 0. So this map is injective. This map must be injective. Okay. So this is the first part. The second part is, I have no time to get into, but we use the second part. I just say, no, I just explain what we do, but now we move from E to the hyperplane. So we have this surface. We have removed some curve, and we have an hyperplane that avoid all this curve. So we would like to show that there exists M big enough such that when we take the form from X to H0 of M times H, so to the neighborhood over this H, this is surjective. Clearly, after some M, it becomes an isomorphism if this is subjective. Then we take a surface in A0 of omega 1 S. And since H avoids all this curve, we can restrict this to H. And it gives an element here. And then we lift to this. But the lifting is stable for all n. But so we have a form alpha such that alpha minus omega restricted to H is equal to 0 in H0 of omega 1 and H. But for this means that in his divisor, there is, in his zero locus, there is MH. But when M becomes bigger and bigger, it means that alpha and omega are equal on the surface. So alpha becomes equal to omega. And then we have lift alpha that was in open space. We restrict to an hyperplane, and then we expand to all the surface. Okay, and then the difference is 0. So we lift to the surface. And this final part, we use the formal function of Grauert, I think, or Grothendieck, to make this. But I made mistake before, so I lost time. Sorry. Anyway, yeah, this final part.
If there is no questions, then let us thank the speaker.